Okay, I've literally never done this before. All you're gonna watch is a ball get really hot and then dropped into water. But you requested it. Yay. This is not as hot as the blowtorch that they were using in the video. That's more comfortable. This is a nickel ball. This is usually done with nickel because it doesn't melt, like in a Bunsen burner. Yep. So anyway, while I'm doing this, let's talk about your test. How'd it go? Good. I thought, oh, not really. What? It is, but it wasn't. Because the stuff we did wasn't new this time. All right, but you can't see your score, I guess, on the internet. Oh, that's weird, because I put it in sixth hour. How long should I do this? It's going to take a long time to get read. I should stand here during lunch. I'm not that dedicated. I could do this and drink Mountain Dew at the same time. Okay, while I'm doing that, let's talk about what most people struggle the most with, which was the bottom of the front page. Now, if you're like, hey, I did a lot better on 1 through 4 than I thought I would, it's because I didn't grade 1 through 4. Unless you left it blank. I just went straight to the top reaction. What number is that? 4B. 4A, I guess. Sorry. So I didn't correct the top 3. This is not comfortable at all. Nope, didn't feel like it. But if you left it blank, you got it wrong. Then the reactions at the bottom. Just looking at Tim's makes me think of everyone that didn't notice that magnesium sulfide was solid. So you put Mg was a spectator ion, but it couldn't be a spectator ion because it was a solid on one side, but it was aqueous on the other. So it was only Cl, right? Are we okay with that? It's like 4B. Okay, then. The other thing a lot of you got wrong, it was which one's the limiting reactant. You put, hey, it's neither because you add the same, but that's false. You needed 3 times the amount of whatever Ba was, right? To aluminum sulfate. It was a 3-to-1 ratio. Then what else? The bottom one, the conductivity goes down because it makes a precipitate and water. A lot of you did not balance at all. You do need to remember, this is probably a way cool video, whoever ended up watching this. You do need to remember to balance charges. Someone just put like phosphoric acid, HPO4. That was really common, but it's H3PO4. And then it reacted with something, I don't remember. But you needed like Al2, no, that's not what it was. Hold on. That one, Al2SO43. All right, I'm gonna just drop this in water. Are you okay with that? Because my shoulder is killing me. We're good. Tim, we'll be all right. Okay, so fascinating. I think that was fun. How did we enjoy that?
That was so cool.
I'll be here all week. Make sure and tip your waitresses on the way out. Okay, so tell your partner what is happening to the ball right now. It's cooling down. The ball represents the what? the system. Okay, the water represents, what's the beaker? What's me? All right, everything except for the system is the surroundings, every single thing out there. Okay, so in consideration with energy and the ball, what sign would it be? Negative, because it makes the water warmer. Now there's a lot of water. It's definitely warmed up, especially down at the bottom. It was at room temperature, right? I happen to have this thing right here, in fact, for a different demo. Let's see where we're at right now. So it was at room temperature. Now it's not a ton higher, but it's creeping up to around 30 Celsius. All right. So that'll just keep on giving off and warming that up. I need this to be back to room temperature though. Don't tell my wife. All right. Okay. So if I had a lot bigger ball and a blowtorch that heated it up to 1200 instead of 600, it probably would have been a cooler demo, but I mean, you asked, and I'm all about delivering your greatest desires, of course. So here we go. Oh, I look good right there. It is my girls' camp sweatshirt. I mean, who doesn't have one of these? Really? Sorry. Okay, I should probably get my butt out of that recording. Let's switch back and talk some notes, and then we'll do another demonstration. Okay. So today, the plan is calorimetry, Hess's law, heats of formation. How many of you did the problem from yesterday? Raise your hands. Okay. Hold on. Okay, how do you feel about those answers? I did those on my prep hour, or on my whatever, while the student teacher was teaching. Do we match? Bill, you raise your hand. Negative 25.48 and negative 12.9. Okay. Well, maybe I typed it in wrong. I did it on a phone, and I don't usually do math on my phone. Did anyone else do this problem? Did you match those? Phoebe?
I completely forgot that so I put 1.
Okay, so here we go. In this problem, you take the given, which was 0.855 right here, and you start with that. It's moles of O2. So I put 0.855 mole of O2 here, but I want to solve for kilojoules. So I have a ratio from the balanced reaction that it's negative 89.4 kilojoules for every 3 moles of O2. So that's why there's a 3 this time. And before, the last one was just 1, 1, and 1, right? All right, so I just take that, multiply it, divide by 3, and I get 25.48. No one had that? Okay, whew. Someone did. All right, then B. This time it gives you grams of KCl. Anytime you have grams, you got to convert it to moles, right? Moles is just dividing the grams by the molar mass. I did it in picket fence form. I did it in picket fence form so I could keep track and make sure I put the 2 on the bottom. That's for my sake, but to help me out. 10.75 grams. I needed to get rid of grams, so I divide by the molar mass. And then I had the ratio of negative 89.4 kilojoules for every 2 moles, because that's what's in front of KCl. Okay, this is, I thought a few more people would participate. What was I thinking? Okay, C says, the decomposition of potassium chlorate proceeds spontaneously when it is heated. That means it is what type of process? Endo. It requires heat for it to happen. All right. Do you think that the reverse reaction is likely to be feasible under ordinary conditions? And the answer is yes. If we had to put energy in for the change, it will give energy back out for the opposite. And that is a likely process to happen. Nature likes to go from high energy to low energy. It wants to give things out. Okay, that's how we did that problem. That's how the three of us did that problem. Okay, now, today, calorimetry, Hess's law, and heats of formation. If we really do this all today, this is like 95% of the test today. I'm excited. Who's excited? Thank you. All right, so now that doesn't mean what we've done was a waste of time. We need it to know what we're going to do. Friday. The test is Friday. Yep. Then we're going to do a calorimetry lab, which is this demonstration on Monday. Yes. No, most kids do the best on this test of the whole try. If you're above a 94 right now, you're going to get an A, like no matter what. Okay, you will. If you're around a 92, then you better get a C or higher. If you're like at a 90, you better get an A, like, or an A minus maybe, because that could offset a lower one. And I had a couple people ask, 90% is the cutoff for an A. If you are above 90.00, you get an A. If you're below it, then you don't get an A, you get the other grade. What? Not in this class. Not in this class. It's in the disclosure. I said it the very first day. The grade book, I can't change it because it's school, but I change it. Like Boxella has its own grading scale. I have to override it by individual person. So even when you get your report card, it'll say like 91.2%, and then it will still say an A. I have to override it. And I will. I looked at the grades today, and only, like, that's a bad way to say it, all but 5 of you have an A. It's there. Okay. Now, some of those non are B's and then other letters. All right, moving on. Calorimetry is not hard. Tim's like, I hate him. I don't know, you just made eye contact with me. It scared me. Okay, calorimetry. Don't write every word down here. But it says, since we cannot know the exact enthalpy of the reactants and the products, we measure delta H through calorimetry, which is a measure of calories or a measure of energy, the measurement of heat flow. Now, I see a ton of you right now. I don't know, there's nothing on this slide really that you should write besides calorimetry is how we calculate heat change. Like I could have just done it with this ball. What you do, as simple as could be, you keep track of how much water you have. You measure its temperature before something happens and after something happens, and you know the change in temperature. If you know the specific heat of water, it is an absolute breeze. It's just a few variables. You can type them in, hit enter, and you move on with your life. Okay, it's really not that bad. This thing right here is called a bomb calorimeter, and we'll never use one, but they are interesting. So a bomb calorimeter, don't stress about this because no high school owns one of these. Well, she said she did one, but no one I've never seen one. All right, reactions can be carried out in a sealed or bomb, such as this one, and measure the heat absorbed by the water. Okay, so what we're doing is we're gonna have, in a bomb calorimeter, it's called constant volume calorimetry, and we're not going to stress a ton about it, but you have something that's going to react and it's going to produce heat. The heat will be absorbed by the water. We'll keep track of how much water there was. what its temperature change was and the specific heat, and it will tell us how much energy was changed. Okay, so this ball, just think about it. If I would have done it, it would have melted right through here though, so it's probably good I didn't. But we could have, without knowing the amount of energy the ball had, we could have figured it out by measuring the temperature of the water before, the temperature of the water after. The temperature rose because the ball gave the water energy, right? We can figure out exactly what that is using this technique. Okay, it's really a very simple process. Okay, now this stuff is interesting, but not, it's going to help us get to the meat of the whole thing. All right, so heat capacity and specific heat, they are slightly different, but very much related. The amount of energy required to raise the temperature of a substance by 1 Kelvin or 1 Celsius is the heat capacity. So if I want to know, I'm going to see how much this is 1, whatever, that's its heat capacity. We define specific heat capacity, or simply specific heat, as the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin. So they're similar, but different. Heat capacity depends on how much stuff you're heating. We have a term for something that depends on how much of something there is. Someone mumbled it. Extensive. This is extensive. So if I want to heat up a small ice cube, it's going to take some energy. If I want to heat up a 10-pound bag of ice, it's going to take more, right? Okay, so that depends on how much there is. So we don't use that very often. We use the specific heat because then it's not amount dependent because it's per 1 gram no matter what. So we define specific heat, once again, as the energy required to take 1 gram of something and raise it 1 degree Celsius. In our world, you've heard of a calorie, and a calorie is exactly that. It takes 1 calorie of energy to raise 1 gram of water 1 degrees Kelvin or Celsius. Would you tell your lab partner why it's Kelvin or Celsius? Okay, I heard a lot of people say the same thing. The change is the same. It's a different value, but the distance of 1 is the same, right? So they are pretty much the same thing. All right, we in chemistry don't use calories very often. We use joules. That's a J. And this is a number you need to know. And that is 4.184 joules. That is the specific heat of water. It takes 4.184 joules to raise 1 gram of water 1 degree Kelvin. So think about that. If I can keep track of how much this mass of water gained temperature-wise, I can just crunch the numbers, right? And it would tell me how much energy the ball lost to the water. Fair enough? Okay. All right, don't write this one down. Don't write this down. It's the same thing. We're going to use it, though, in a different way. So specific heat is the heat transfer divided by the mass times the temperature change. That's fine, but we prefer, oh, maybe it was lower. This is not how we prefer it. I would not, it's the same thing, but I want you to memorize that Q equals S M delta T. Yep, because it almost always wants you to solve for Q, the heat. It will give you S in the problem. So this is an equation you'll use a lot. All right, so let's chop this up. I swear I had a slide. It's probably later for some reason and I lost it. All right, so Q is the heat, and really Q is the enthalpy because they're the same, right? As long as there's no work involved. And there is no work involved here. The heat, or delta H, is equal to S. That's the specific heat. And that's 99% of the time given to you, or you have to look it up in a table. But it's not math, like you'll have to calculate specific heat. It's given to you. All right. This is times the mass. And it's the mass of the thing that you have the specific heat of. They have to match. It's not usually the mass of just like the ball. It's the mass of the water, because I found the specific heat for water. So I'm going to take the mass of water. And then delta T is your change in temp. And that needs to be in Celsius or Kelvin. All right, while you're writing that down, I'm going to pour some stuff. All right. So I have a pretty simple demonstration here. I don't know how well the camera will do, but it's okay. Okay. So I was hoping the camera would show you. It did before I messed with it. Hold on. Oh, come on. You still can't see it very well, but just trust me. We okay with that? Trust. Okay, this is on a hot plate, but the heat is not on. It's also a stir plate. So I have a little magnet in this cup spinning around just so it mixes evenly. You okay with that? Let me lower this down. It's so bright. Xander, will you turn the light off and it might focus better? Just the top or the bottom one. Try the bottom one first. Better? Okay, both of them. Let's try it. It's just, yeah, that's all right. Turn one of them back on and we'll see if I get it to focus on the remote. Okay, good enough. It is right now. It's on your side. I can't even find it. Excuse me. All right, we are at 22 degrees Celsius. You okay with that? How'd the back of my head look, Tim? Okay, write that down. 22 degrees Celsius. We're going to need that information. Okay, I don't know which one, but that's either hydrochloric acid or sodium hydroxide. And I should have taken the temperature of that, but they've all been sitting at room temperature, so we'll still assume 22. You okay with that? Okay, and I added, it was at 40, so I've added 40 milliliters. We're going to assume, and this is an assumption you can't always make, we're going to assume that it's a density of 1. That way the milliliters and the grams are the same. I'm adding 40 and 40. So what's my total mass going to be? 80. If the density is 1, the volume and the grams are the same. Thumbs up on that. If it's not, you need to figure out what the mass is from the volume, just using D equals M over V. Okay, now I'm at 22, and now I'm going to add either base or acid because I didn't keep track of which one I put in first. What? What did I say the other was? Okay, then this is sodium hydroxide. So we'll add this in. And then I'll just kind of keep track of the thermometer. You can't see it, but it's already at 30. It's at 32. Can you see it going up? Okay, all right, you can see it. All right, so it went from 22, the angle might be weird, but it is a little above 35. We'll just call that good. It doesn't seem to be moving anymore. Okay, so 22 and 35. Definitely a heat change, correct? Tell your partners whether that reaction that just happened was endo or exothermic and tell them why. Okay, it was exothermic, which means it has what sign? It has a negative sign because your X was hot, but really a negative person. So you just hit the road. All right, let's share this again. Okay, so we're just going to do some pretty simple math. It really is. The specific heat of water, we are going to memorize it. It is 4.184 joules. You okay with that? All right. What was the mass? It was 80 grams. What was the change in temperature? What's that? All right, it was 13. Someone multiply that out for me. We'll talk about that. $4,000 should probably be close. 4351. 0.1. You okay with that? Okay, the question was asked, should it be a negative 13? Well, it's final minus initial, isn't it? That is a positive value, but this should be exothermic, correct? All right, so here's how this really works. I don't teach it like this, but it is really negative SM delta T. But I don't want you to even do that. I've learned over time that that will screw you up with how you find the temperature and if you're asked for the mass. So all I want you to do is if you know the temperature got hotter, it's an exothermic process, right? So you answer very carefully. You would say 4,351.4 joules were released. Don't ever say negative 4,351.4 joules were released. And the reason you got to be really careful is because the question, especially in the AP test, it's going to ask you like the energy absorbed or released. And you can put a sign, but I would write it as a sentence because there's no doubt here what you meant, right? Okay, so very not awful, I hope. The equation Q equals SM delta T. So we have it right there, 4351.4. Now that seems like a big number, but that's actually a really small number because that's in what unit? Thank you. It's joules. But almost everything in our life, we use kilojoules. So it's really 4.351 kilojoules. It's not that much energy, even though it seemed like a big number. Be careful on these questions when it asks. Make sure that you have the correct unit. If it's kilo, move it over 3 times and it comes smaller. If it's not kilo and you have it, move it to the right 3 times and it gets bigger. You okay with that? Okay. There was just an example instead of me doing it. Okay, I guess I went a little out of order, but it doesn't really matter. We will always do constant pressure calorimetry, which is this, meaning it's in an open container. They often call it a coffee cup calorimeter. In Utah, we call it a hot chocolate cup calorimeter. All right, but all it is 2 cups that are insulated so heat isn't lost to the cups. The exchange is really just in the water and the system. You okay with that? Okay, very often they'll ask you to draw a calorimeter, and it's a cup with two things coming out of it. One's a thermometer and one is, whoops, the stirrer. I didn't have the stirrer in here because I have a magnetic stir thing, but it just looks like this. You would just put it in there and you could stir it around. Whatever. It's a pretty easy thing to draw, a cup with two things coming out of it. Usually you'll have something on the top, but there'll be holes like a cork. We don't want pressure to build. It's just there to insulate it even more. Because when I added this, some of the heat was lost to the atmosphere, right? They want to make it as precise as possible. And in bomb calorimetry, they can be extremely precise. In coffee cup or constant pressure calorimetry, we're not as accurate, but we're talking like tenths off. It's not that big of a change. Okay. Oh, I knew I had it later. So there's our equation. Q equals, that one has ms delta T, but it doesn't really matter. Okay with that? Okay, so steps to solve calorimetry or calorimeter problems. Use Q equals, oh, I don't teach this way anymore. So I'm just gonna get rid of that. Are you okay with that? Like it makes sense, but really the way the questions are asked, just do the math. And if you know it released heat, then it was exo. If it took in, endo. Okay, remember to make sure M is the mass of the entire solution. So I didn't use just the 40 of my HCl or the 40, I added both. Okay. Convert to kilojoules. This is, oh, hold on. We need to do a problem first. Here we go. We'll go back to that as we work through this problem. I'll go back, I promise. Okay. So 30 grams of sulfuric acid is added to 250 milliliters of water. The temperature rises from 23K to 31K. I should tell you, if this was the AP test, it would have to say another sentence right here. Any guess what this sentence would be talking about? The density. So it would say, I'll just make it up. The density, whatever that says density, of the solution is 1.108. They would have to add that because you couldn't technically do that with that, do this without it. Okay, so what is the heat gained or lost in this process? So that's Q. Tell your partner what Q is equal to. What letters? S. What else? M and delta T. So Q equals 4.184 because that's what S is going to be. If it's not water, the problem has to give you that. Okay. 4.184. Then the next part is the mass, correct? So the mass, we need to do a little calculation before we go in there. So how many total, oh, it says 30 grams. That's just stupid. Yeah, but it just doesn't work with the way I want it. I'm going to say it's milliliters because it would be milliliters too. This is the more likely scenario. You okay with that? Okay. Okay. So the way it's written, it was easy. I wouldn't need the sentence. I just should have read careful. But pretend now we have 30 milliliters. So we have, just do it right here, 280 milliliters. How do I find how many grams that is? So if D equals M over V, what is M? It's D times V, right? You with me? Who's with me? Okay. So 280 came from 250 plus 30 milliliters. I hate when I screw up, but it's okay. So I take my 280 and I multiply it by 1.108. Anyone have that for me already? All right, 310 point what? 24. So I have S, I have my M, and now I just need my delta T, which is, all right, 8. So we would multiply. Did someone ask me something?
I started to, but then I was starting to as well.
Okay, what number do we get here? 1,000.
10,384.35.
All right. Now, it says, what is the heat gained or lost in this? You would say 10,384.35 joules were, okay, released or lost to the system. Not lost like, oh no, where'd they go? Or sorry, to the surroundings, to the surroundings. I hate when I say it backwards. Yep, and you'll want to for the next problem. So this is really 10.384 kilojoules. And if we're really being technical, it's 10. Because sig figs. But we'll go with 10.384. That works good enough. Okay, part B says, what is delta H in kilojoules per mole for the dissolution of sulfuric acid? Well, I don't know, IDK. Well, what I just found out, and why am I so dumb here? We're going to go back to pretend this is grams. Okay. What we just found out is that for every 30 grams H2SO4, I can get 10.384. But this wants it per 1 mole. How do we convert moles to grams? Molar mass. H2SO4 is 100. It's either 98 or 100. 64, 32, 98. Anyone back me up on that one? Thank you, Bill. Okay, so it's 98. You with me? Okay, so I could do this in picket fence, or I'm just going to take 30 and divide it by 98 grams. And what does that equal? What's that? All right, now I want this in kilojoules per mole. This is kilojoules. So what do I need on the bottom? 0.306 moles. I don't need this on anymore. So 10 divided by 0.306 ends up to be what? $33.5? Okay. So a little weird. I found it for a certain amount, but I need to know what it is per 1 mole. So I keep the kilojoules I made and I divide it by the moles that I had. And that will convert it to how many there are per 1 mole. Sort of. Okay. Coming down, there's more. How many grams of sulfuric acid would you need to raise the temperature of 425 grams of solution 20 degrees Celsius? All right. Any ideas what to do here? Go ahead. He's right. That's the hard way to do it, which is fine. You can do it that way. That works. What I would recommend, you end up with 425 grams. You need to find out how many moles this is. How do you do that? The molar mass. So 425, you can divide it or picket fence it, 98 grams. You have 1 mole here. What do you get there? 4.3 moles. You okay with that? Okay. Then that needs to be multiplied by the number we just found. For every mole, there are 33.9 kilojoules. This is tricky. I know there's a lot of steps here. We'll do a bunch of them, so don't stress. You don't have that answer for me? Yeah, it's got to be way bigger than that. 145. .7 kilojoules is the amount of energy that we need, right? Is that what I want, though? I want grams and I want it per 20. All right, for 20 Celsius. So this is now what I have. I have an equation that says Q equals SM delta T. Anyone know what this is? That's Q. Now, trust me, we'll do another one. I know this is a ton of steps, but they'll come together. This is Q. But S is in what unit? Who's got me on that one? Joules. This is in kilojoules. Are you okay if I say 145,700 joules equals 4.184? What's the mass? All right, what do we have here? I have 20. Now, there's a big weakness in me just typing this problem up that I've noticed. We'll just pretend it works and I won't tell you what it is. It's still fine, we can do it. There's a little error. All right, what do we, wait, whoa. Sorry, that's not 425. We're solving for that value. I'm sorry, we're solving for that value. My bad. Okay, so how would we solve for that X? Whoops. There's a lot, I know. But it'll come together usually pretty quick after we do a couple of problems. So I have 145,700 divided by those two numbers. What do I get?
41.
All right. Was that a ton of fun? How many think you could do it now? 2.5 of you. All right. They are tricky. The good news is usually we end here. C is great, but usually you don't see that on the AP test. Now on my test, if I remember right, it is there. I'll look, but we'll do a couple practice with them. So the first step we did, you got to find the heat per the given. The next step is we convert them to kilojoules and divide it by the moles we were given. The third step is to use our now kilojoules per mole and solve for the heat required, and then solve S equals M delta T. Okay, going back here, there's a lot here. That may not go in the same order, but it's okay. So to do these problems, we use Q equals SM delta T. Remember to make sure M is the mass of the entire solution. All right, convert to kilojoules. Find the moles of solute given by dividing the given mass by the molar mass of the solute. How about tomorrow I'll print this page and we'll work through a problem together with it. Yeah. All right, because it'll take you more than the 2.5 minutes we have left to do that. Now, Jackson, I have no problem finding the mole to whatever ratio and that whatever ratio and working that. No problem. You'll get full credit for doing it that way as well. Okay, I knew we wouldn't get through all three, but what we have coming up is Hess's law, which is not hard. It's like saying that the amount of energy required to go up 3 steps is the same as each step added to each other. That's literally it. And it's like, how did a guy get that named after him? I don't know either. Okay, we'll do that. And then we will do some heats of formation. I promise you that I know right now you're like, I don't know what's going on. But we're going to do practice problems after practice problems. So Friday becomes automatic. It's Friday. Oh, sorry, this is from last year. It's actually from 2 years ago. You do? All right, I like that. See what happens when you come for the whole lecture? It's weird.